Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Electron Beam Lithography, that is EBL, from the paper Nanoscience and Nanotechnology. So students, let us see what we are going to learn in this module. In this module, electron beam lithography technique is described. Also, E-beam lithography system is discussed in detail with a description of electron sources, lenses, stage, alignment, electron beam, right time, short noise, etc. In addition, the process of electron energy deposition is studied along with the resolution capability, scattering, and proximity effect. Finally, the charging phenomena is also discussed in this module. Now beginning with what is electron beam lithography? Electron beam lithography or E-beam lithography is a technique which is used to draw patterns over a substrate by using focused electron beam. The surface of the substrate is covered with an electron-sensitive film, which is also termed as resist. It does not deposit the material onto the surface, rather it changes the solubility of the resist which is already present on the surface. On exposure to the electron beam, the solubility of the resist changes such that the resist can be selectively removed, wherein either the exposed part becomes more soluble or the unexposed part becomes more soluble, which ultimately depends on the type of resist. The resist can be simply removed by immersing it in a solvent, which is often termed as developing. Similar to photolithography, small features are created in the resist and then subsequently transferred to a substrate via etching. The most important advantage of E-beam technique over standard photolithography is that it can draw patterns with nanometer resolutions. E-beam is a maskless technique which is having high resolution and low throughput. As a result, its use is limited to fabricating photomask, producing semiconductor devices in low volumes, and research and development activities. We will now discuss the electron beam lithography systems. Electron beam lithographic systems employed for commercial applications are dedicated electron beam writing systems and are very costly. The cost is greater than $1 million. For research purposes, an electron microscope is usually converted into electron beam lithography system by attaching additional accessories which are relatively inexpensive, of the order of $100K. Although these converted systems do not achieve the resolution which is inherent to electron beam lithography systems, they still manage to get approximately 10 nanometer line widths. The classification of electron beam lithography systems is based on the beam shape as well as the system which is used for beam deflection. Earlier systems were based on Gaussian-shaped beams and raster scanned the surface. Modern systems have shaped beams which can be vector scanned, that is, deflecting the beam to multiple positions in the writing field. Let us discuss the various electron sources. Systems having low resolutions use thermionic source, which is made of lanthanum hexaboride. To achieve high resolutions, field emission sources, example, heated tungsten zirconium dioxide for low energy spread and enhanced brightness. There are two types of field emission sources: thermal and cold emission sources. The beam size is bigger in thermal emission sources in comparison to the cold ones. However, owing to the better stability for prolonged writing times, thermal field emission sources are usually preferred. Lenses. Coming on to lenses, electrostatic as well as magnetic lenses may be used. But due to more aberration, electrostatic lenses are not suitable for fine focusing. Since chromatic electron beams are not produced currently, very fine focusing is achieved by using extremely narrow dispersion of electron beam energy. We will next discuss about the stage, the stretching and alignment. Electrostatic lenses may be used for very small beam deflections, whereas electromagnetic lenses are required for large beam deflections. Due to the inaccuracy and finite number of steps in exposure grid, the writing field is around 100 microns to 1 millimeter. Stage needs to be adjusted for drawing large patterns. Accurate stage positioning is critical for stitching, that is, tilting writing fields exactly against each other, and pattern overlay, which is aligning a pattern to the previously drawn pattern. Figure 1 shows the schematics of field stitching. It is a major concern for critical features crossing a field boundary, which is shown by a red dotted line. We will next move on to study the electron beam write time. Minimum time which is required to expose a given area can be expressed as d into A equals T into I, where the object needs to be exposed for a time t and can be further divided into exposure time per unit step size. I represents the beam current, D is the dose, and A is the exposed area. As an example, consider an area of 1 centimeter square which is exposed to a dose of 10 raised to the minus 3 coulomb per centimeter square at a beam current of 10 nanoamperes. The time required to write as calculated from above equation is 10 raised to the 6 seconds or approximately 12 days. Additional time is needed for stage adjustment, time required to blank the beam, that is blocking during deflection, etc. Similarly, to cover 700 centimeter square of a 300 mm silicon wafer, writing times is around 22 years. Thus, throughput is a serious concern of E-beam lithography, and it is worse for creating dense patterns over larger areas. This seriously precludes any commercial scale production using this technique. A small field of electron beam used to write the pattern makes this technique very slow in comparison to the standard photolithography. Due to the small size of electron field, More exposure fields are needed to scan for creating a pattern. For comparison, the field size is less than 1 millimeter square in electron beam, whereas it is greater than 40 square in optical mask projection scanner. Further, the stage also moves in between field scans. Due to the small size, raster scan is required to create patterns. Example, for a 26 cross 36 pattern in E-beam, whereas in photolithography, only one-dimensional scan is required for this purpose. Presently, for a given resolution, optical maskless lithographic tool is much faster than electron beam tool in patterning a photomask. Let us next discuss about the shot noise. With a reduction in feature size, there is a corresponding decrease in the number of incident electrons for fixtures. When the number of electrons approaches 10,000, shot noise starts dominating, resulting in significant variations in the dose within a large feature population. The features are decreased by half with each successive process node. Thus, for keeping the noise level at its previous value, dose must be doubled. This results in decreasing the throughput by half with each successive process node. Shot noise needs to be considered for mask formation as well. For instance, commercial mask electron beam resist such as FEP 171 uses doses below 10 microcoulomb per centimeter square. This results in substantial noise for a target CD even of the order of 200 nanometer on the mask. There are still two types of data related defects. First one is the blanking of deflection and second one is the shaping errors. Blanking errors are related to the improper deflection of the electron beam. Whereas, if the projecting shape is not correct, shaping errors occurs. Data errors may be caused by either electron optical control hardware or input data which taped out. These errors are more dominant in large data files. There are several types of physical defects such as charging of the sample, which is both positive or negative, backscattering calculation errors, dose errors, outgassing, fogging, long-range deflection of backscattered electrons, errors due to contaminants, drift in beam, etc. Because E-beam takes a very long time for creating patterns, random errors are more frequent. This possibility is more for large data files. Majority of the photomask defects occur while E-beam lithographic processing is employed to define the pattern. We will next study the electron energy deposition. The incident electrons may undergo inelastic scatterings and collisions with the electrons present in the target material. In this way, the incident electron loses its energy. Figure 2 shows the possible trajectories of electrons in a resist. An incident electron, which is red, creates the secondary electrons, which are blue in color. The incident electron may also get backscattered, thereby leaving the resist. Now, during collisions, incident electron transfers its momentum to the electron present in an atomic orbital of the material. The transfer momentum is given by dp equals 2e square by b nu, where b is the distance of the closest approach between the electrons. V is the velocity of the incident electrons. The energy transferred via collision is G equals dp whole square by 2m. This equals e raised to power 4 divided by capital E into b square. Here m is the mass of electron and capital E is the energy of the incident electron, which is given by E equals half mv square. Due to the use of double patterning, the spacing between the features could be increased so as to reduce the scattering of secondary electrons. The use of high energy electrons and thin resist can reduce the forward scattering. However, secondary electrons occur inevitably. Low energy electrons have been found to travel large distances, that is, several nanometers, in insulating materials, for example, PMMA. This mainly occurs because below the ionization potentials, energy can only be lost via phonons and polarons. Even though polarons are ionic lattice effects, they can exhibit long-range hopping, that is, up to 20 nanometers. The distance which is covered by a secondary electron is not physically calculated value, but it is usually estimated experimentally or Monte Carlo simulations below 1 electron volt. That is, energy distribution in secondary electron peaks much below 10 electron volts. Thus, the resolution limit is not cited as a fixed number like an optical diffraction limited system. Resist development and intermolecular forces are important to the image formation. We will next discuss about the resolution capability. Aberration as well as space charge limit the electron beam widths, which are of the order of few nanometers. But the feature resolution is not affected by the beam size. Rather, it depends on the forward scattering, that is effective beam broadening in the resist. In addition, the pitch resolution depends upon the propagation of secondary electrons in the resist. This was demonstrated in year 2007, where E-beam was used for double patterning to fabricate 15 nanometer half pitch zone plates. In this study, the 15 nanometer feature could be easily resolved, whereas a 30 nanometer pitch could not be achieved. This was caused by the scattering of secondary electrons from the adjacent feature. Due to the use of double patterning, the spacing between the features could be increased so as to reduce the scattering of secondary electrons. The use of high energy electrons and thin resist can reduce the forward scattering. To mask, these electrons take longer time to reach the electrical ground. A secondary electron emission in vacuum can be used to provide counter, that is positive charge, to avoid negative charge accumulation on a substrate. The use of thin conducting layers above or below the resist cannot solve the charging problem completely, as the high energy electrons may penetrate through these layers to reach the substrate. The charge dissipation layer can also be used up to 10 kilo electron volt because due to the thinness of resist, the majority of electrons stop either at the resist or near the conductive layer. The large resistance of these conducting layers may significantly obstruct the path of electrons towards the ground and thus these layers are of limited use. The low energy secondary electrons, which is the largest portion of the free electron population in the resist substrate system, contributing towards changing, do not have a fixed range, usually vary between 0 and 50 nanometer. This leads to inconsistent resist substrate charging, making it difficult to compensate. The accumulation of negative charges causes deflection of the electron beam away from the charged area, whereas positive charge accumulation attracts the electron beam. We will next study the electron beam resist performance. Since the scission efficiency is usually an order of magnitude higher than that of cross-linking, so majority of the polymers which are used for positive tone E-beam lithography will cross-link and become negative tone at a dose an order of magnitude higher than the dose which is required for positive tone exposure. Such large dose increases may be needed to prelude the impact of shot noise. It has been reported that low energy electrons can damage PMMA films of up to 30 nanometer thickness. The damage was in the form of material loss. Other observations may be summarized as follows. First, for ZP520, the frequently used resist, the pitch resolution limit was achieved in 60 nanometer, that is 30 nanometer lines and spaces, and this value did not depend on thickness of the film and energy of the beam. Secondly, if the resolution was increased to 20 nanometer by using a 3 nanometer 100 kilo electron volt E-beam and PMMA resist, 20 nanometer unexposed gaps between exposed lines showed inadvertent exposure by secondary electron. Then the hydrogen silicizane negative tone resist can produce isolated 2 nanometer wide lines and 10 nanometer periodic dot arrays, 10 nanometer pitch in very thin lists. HSQ is like porous hydrogenated SiO2 and can be employed to etch silicon but not the SiO2 like dielectrics. We will next discuss the new frontiers in electron beam lithography. To avoid the creation of secondary electrons, low energy electrons may be used to irradiate the recent secondary electrons. Thus, these electrons will not have enough energy to generate secondary electrons. This has been successfully done with the SGM as the beam source. Observations have shown that electrons having energy around 12 electron volts penetrate a 50 nanometer thick layer of polymer resist. However, low energy electrons spread in the resist. Furthermore, the use of low energy electrons seriously limits their resolution. Additionally, low energy electrons also suffer the most due to Coulombic repulsions from other electrons. Figure 3 shows the scanning probe lithography, which can be used in low energy E-beam lithography. The resolutions reached via this technique are of the order of 100 nanometer and are influenced by the dose of low energy electrons. We will next discuss about the proximity effect. Proximity effect results when the electrons from a nearby exposed region reach the current pattern to be created and cause enlargement of the new feature. It also decreases the contrast of the new feature to be created. Usually, the electron beam lithography is employed for creating isolated features since the cascaded features exaggerate the proximity effects. Thus, the feature resolution in case of nested or cascaded features becomes very hard to control. For most resists, it is difficult to go below 25 nanometer lines and spaces. Proximity effect gets manifested when the secondary electrons leave the top surface of resist and they come back at some distance of the order of 10 nanometer. Scattering-induced proximity effects can be addressed by solving the inverse problem to calculate the exposure function E of xy, which results in a dose distribution to the closest desired dose, that is g of xy, when convolved with scattering distribution point spread function, that is PSF of xy. Noticeably, any error in the dose, which may be due to short noise, will lead to failures in correcting the proximity effects. Alternatively, very high energy electrons, which are greater than 100 kV, can be used to effectively drill or sputter the material. It is commonly seen in transmission electron microscopy. Nonetheless, it is an inefficient process because the momentum cannot be transferred effectively from the incident electrons to the material. Consequently, the process is very slow and it requires prolonged exposure duration in comparison to the conventional electron beam lithography. Besides, the substrate may get damaged due to the high energy electrons being irradiated onto it. Arrays with nanoscale periods can also be patterned using electron beam interference lithography. The main benefit of electrons over photons in interferometry is the short wavelength of electrons for a fixed energy. Regardless of the above mentioned complexities which are involved in electron beam lithography, it still is a widely used technique to concentrate maximum energy into a smallest area. There have been continuous efforts towards increasing the throughput of this technique. Another concern which is involved is the high cost of the equipment. So students, let us now summarize what we have learned in this module. In this module, electron beam lithography technique was described. Also, electron beam lithography system was discussed in detail with a description of electron sources, lenses, stage alignment, electron beam write time, short noise, etc. The process of electron energy deposition was studied along with the resolution capability, scattering, and proximity effect. Finally, the charging phenomena was also discussed in this module. Thank you students for your attention.